Hi there. In this video I'll show you the application of a data-driven control method that we devised recently to a very important application, which is the voltage control in an uninterruptible power supply. And this control method, the control design method that we developed, is what we call a vintage data-driven control method, because it's based on the very classic Ziegler-Nichols approach to data-driven control design. In this presentation, I'll first show you the plant we are going to control, which is the uninterruptible power source, then what are the specifications for the control design, and then the design itself. And after performing the design, I'll show you the closed loop performance that we get with this data-driven design. This is the plant, and you have a picture of the actual plant here. It is an uninterruptible power source that we also call an UPS. An UPS is an electronic device that provides AC power. In this case, this is a UPS, a commercial UPS that has 3.5 kilovolt ampere in a single phase UPS, and this is the one we're going to apply our design to. The specifications for the control design are that the UPS must sustain its sinusoidal voltage form with constant magnitude and frequency, no matter the disturbances. And the disturbances are typically connection and disconnection of loads, and the fact that you have nonlinear loads. This is very common in most applications. And there are norms that specify how a commercial UPS must behave. And the norm we follow for this design is the norm whose name you see on the screen there. In mathematical terms, the specifications translate as follows. We need to track a sinusoidal reference and with a 60 Hertz frequency and 127 volts of amplitude, and we must reject disturbances that are harmonics of this sinusoidal reference signal. And we must reject the first, third, and fifth harmonics. And from a transient, these are steady state specifications. From a transient point of view, the norm tells us how the UPS must recover its voltage from connection, disconnection of loads. And these must be done within times that are specified in a very specific form by the norm. So these are specifications we have to follow, and the control setup is as follows. We actually have two control loops. One is the main control loop that is represented by the control C of S, as you see in the figure. And the other one is a current control loop, which is represented by the proportional gain Kc you see in the figure. And the current control loop is an auxiliary loop that helps improve the transient performance. So we have to design these two controllers. The first one, the proportional controller Kc, and the other one, the controller C of S, which is the main loop. And so we must design the control C of S, and from basic control theory we know that to satisfy the steady state performance requirements, as I just showed you, the controller must have the form you see on the screen. C of S must be the product of three factors like the ones you see on the screen, where omega R, recall omega R is the frequency of the signal you have to track. So you have the parameters A1, B1, C1, A3, B3, C3, etc. These are 9 parameters you have to tune in order to satisfy the transient performance specifications. And besides these 9 parameters, there is the gain Kc of the auxiliary loop. So we have 10 parameters to tune. And no matter what these parameters are, the steady state constraint specifications will be satisfied. These parameters must be tuned in order to satisfy the transient constraints. So now the design method is based on the Ziegler-Nichols, let's say, philosophy, which is the most ancient philosophy for control design you have. It's been around since the 1930s. So this is a control design method that is only data-driven, the classical Ziegler-Nichols control method. And this method I'm going to present right now is a more sophisticated control design method than the Ziegler-Nichols control. in the sense that it applies to this controller, which is much more complicated, much more complex than the ones the Ziegler-Nichols, the classical Ziegler-Nichols methods apply to, which is only to PID controllers. And so what we do is we perform a relay, what we call a relay feedback experiment, but not a traditional relay feedback experiment, but a relay feedback experiment with what we call the relay with adjustable phase, the RAP, what you see on the screen. The RAP is a relay with a transfer function in series with it, and this transfer function is actually a fraction order integrator, such that its phase is constant for all frequencies. And we perform this experiment first for the inner control loop, which is the auxiliary current control loop, and then for the outer control loop, which is the main control loop, the voltage control loop. And this experiment consists in changing the phase of the transfer function f of s from 0 to minus 60, then to minus 120 degrees. And this can be easily, very easily automated, and that's what we have done. So we start the experiment with phi equals to 0, then you check, then you wait to see if an oscillation occurs. If it does occur, you say that the process you are going to control is a process of what we call class A, and then you measure the amplitude and period of this frequency. If an oscillation does not occur, you reduce the phase to minus 60 degrees, and you do the same. If a sustained oscillation occurs, then this is a class B process. If it does not occur, then you reduce the phase once again to minus 120 degrees. And you do this automatically until a sustained oscillation is obtained. And then once you have done that, the oscillation you have observed, from the oscillation you have observed, you measure the amplitude and the period. So we have done this for the UPS, for our UPS, and we have verified that the inner plant, which is the current control, is of class C. That means that it only oscillates in the third step of the experiment. And then we take this oscillation that we have observed, and we measure the amplitude and the period. You see the oscillation we have measured. These are the actual measurements you see on the screen. Amplitude is 43 amperes, and the period is 2.7 milliseconds. Then we do a second experiment for the outer loop. And the outer loop, we see that it's of class B, which means it starts to oscillate at the second step of the experiment. And then we get the oscillation you see on the screen. Again, these are the actual measurements, and you measure the amplitude A and the period T. From these measurements, these two amplitudes and these two periods, you're going to have formula for all the 10 parameters that you have to tune. And these formulae are a part of the method. There is a table with the formula that we have derived previously. So in the application, when applying the method, you only have to measure and consult the formula. So for each control loop, what you do, you take the measurements T and A, you calculate this omega, and this M, you see this formula you see on the screen, and then for each parameter you have to tune, you have a formula involved with this M and omega. And for each process class ABC and each controller type, whether it's a proportional controller, PID, a PR, or in this case of our application, a multi-resonant MR controller, the formulas are different. So for the current controller, which is a proportional controller, the formula is just 4.5, as you see on the screen, divided by the M you just calculated. For the controller, for the multi-resonant controller, you have all these set of formulas. I'm not going to bother you with all the formulas. You can check the formulas and where they come from in our papers that we reference our review to. So the formulas are like this. You see, you have such formulas. You just have to calculate the parameters A1, B1, C1, so on till C3, and the design is ready. So what you have done is you perform one relay with adjustable phase experiment in the inner loop, another relay with adjustable phase experiment in the outer loop. You measure A and T, you calculate M and omega go into this formula, and the design is ready. Now we use the controller thus designed in the UPS, and we perform the tests that the norm tells you to do. The norm has a bunch of standard tests that you have to submit the UPS to, and in these tests you must perform according to what the norm specifies. So the first test is a steady state analysis with the nominal load with a maximum nonlinear characteristic. And in this worst case scenario, there is a maximum total harmonic distortion that the voltage can have. And the total harmonic distortion we have obtained is 0.45%, which is well within the norm. You see the curve on the screen. These curves are the voltage and the current. The one that looks sinusoidal, though not so much, is the voltage. But again, this is the worst case scenario for the voltage. And you see that it's within the norm with 4.4% of total harmonic distortion. And the other test is a test where you verify the transient behavior after you increase the load or decrease the load. And in this situation, there are these lines. You see, this is a transient. This is a transient of the voltage, and the voltage increasing the load and decreasing the load. In both cases, the voltage must lie in between these two dashed curves. And you see that with nominal voltage and with nominal load, sorry. And you see that with our controller, that's what happens. It's well within the norm again. So this is what we call a vintage data-driven control design method, in which you have these standard experiments to collect this simple information from the plant. And from this simple information you obtain in these experiments, you have this formula for the parameters.